Good morning, students. In today's video, we will study about Gauss Theorem, and from Gauss Theorem, we will derive Coulomb's law. What is the connection between Gauss Theorem and Coulomb's law is going to be our study. Now, in the previous video, we studied about Gauss Theorem. Gauss Theorem talks about surface integral of electric field, that is integral E ds over a given surface is equal to, what is the surface integral equal to? The electric field and electric flux comes out because of the charge, right? The charge enclosed in a given surface divided by the constant epsilon naught. Now EDS, this is EDS, integral EDS is nothing but electric flux. We studied about electric flux, which is the number of electric field lines passing through a given surface which is held perpendicular. Fine. Now we have to derive Coulomb's law. We know Coulomb's law that electric field is equal to 1 upon 4 pi epsilon naught into Q upon R square. Right? This is the electric field, and you wanted to have the force. Let us say electric field is equal to force upon the test charge. So we can say from this force is equal to Q naught into E. Now how to derive that equation? This is what we are going to study in this particular video. Now I have taken a point charge. The point charge, I have to assume a Gaussian surface. What is a Gaussian surface? Gaussian surface is an imaginary surface. First remember, it is an imaginary surface and it is symmetrical with respect to the charge you have been given. And I have taken a point charge. So I consider equidistance from the point charge. Fine. And when I see that a sphere will be a Gaussian surface, a better Gaussian surface will be a sphere. You can take it, for example, a ball like this, right? The ball is a sphere now, and the charge is at the center of this ball. Fine. So the Gaussian surface is the sphere. Now we are going to talk about the electric field. So E into integral ds over the given surface is equal to Q upon epsilon naught. Q is the charge already there. Fine. And the Gaussian surface is a sphere. Now what is the surface area of a Gaussian surface? Surface area of the sphere here. Sphere, the surface area is 4 pi r square. 4 pi r square is that of the sphere. It can be a cylinder. It can be any other shape. But in this case, according to the symmetrical point of view, the charge is here and the Gaussian surface is a sphere. So we will take the Gaussian surface area to be 4 pi r square multiplied by, that is equal to Q upon epsilon naught. In the next stage, we will take the electric field is equal to, take it here and bring 4 pi r square down here, 1 upon 4 pi r square into Q upon epsilon naught. Now we will just rearrange that 1 upon 4 pi epsilon naught into, this has come over here and r square I take it there, Q upon r square. Or you see that electric field is equal to 1 upon 4 pi epsilon naught Q upon r square. So Gauss theorem is a simplistic form of Coulomb's law. In Coulomb's law, the charges are so many are there, so the calculation becomes cumbersome, very difficult. But when you take Coulomb's law, it becomes very easy because we are using the concept of integration or summation. I hope you understand this point. Now electric field value, when I substitute it here, 1 upon 4 pi epsilon naught into Q naught, right? Q naught upon r square, and this is nothing but the force due to using the Coulomb's law. You understand now? So in either way we can do it. From Coulomb's law we can derive Gauss theorem, and from Gauss theorem we can derive Coulomb's law. In today's Another topic let me introduce to you. It is about distribution of charges, right? So Gaussian surface is an imaginary surface. Fine, that you have to remember very carefully. And all the points on the Gaussian surface, the electric field is constant. All the points on the Gaussian surface, the electric field is constant. And the electric field is normal at every point on the Gaussian surface. These are the 3 points which you have to keep it in mind. One is, if I take this is the charge, let us say plus q or minus q, and the Gaussian surface is a sphere. It is symmetrical, equidistant from the charge, that is point 1. Point 2, at every point, the electric field is perpendicular to the point. Yes, these 2 points you have to remember. And the intensity of the electric field at every point is also constant because it is lying at a equidistance. And let us learn a small concept called distribution of charges. Distribution of charges. What are the different ways in which we can distribute a charge? One is called line of charge. Line of charge. And second is called area of charge. Charge distribution over an area. And volume of charge. Distribution can be done in 3 ways. Line of charge, it is a single line. It is only one dimension. The charges are being spread on that, let us say, a line of charge on a wire, you can imagine. Fine. And here the charge density, we take it as lambda Coulomb per meter. It is a line, so in 1 meter you can place lambda Coulomb of charge. Okay, this is the charge density. We use the word called charge density. And in the second case, area of charges. Let me assume an area, a rectangle or whatever it is where I have spread the charges. Here the charge density is taken as sigma Coulomb per meter square. Again meter square, that means in 1 meter square of an area, sigma Coulomb can be placed. And volume is nothing but a sphere or shell. You think on that, it can be a solid sphere or it can be a hollow sphere, and you place the charges over that. And here we take rho Coulomb per meter cube. That means in 1 meter cube, the charge density is rho Coulomb. So there are 3 ways of charge distribution. You can distribute a charge, it's all static electricity, right, on a line, so lambda Coulomb per meter, or on an area, then it is sigma Coulomb per meter square, or a volume, that is rho Coulomb per meter cube. In the next class, we will study about line of charge with another example. Thank you.